Hello everyone, and welcome to this video, which is an introduction to HFSS. So HFSS will be the software that we will use for the project in ELEC3909. So before going into HFSS, I would like to give you an introduction to what it is. So HFSS stands for High Frequency Structure Simulator, and it's a software that's part of the ANSYS electronics desktop package. HFSS is used to analyze structures from an electromagnetic perspective. For example, it's used to calculate electric and magnetic fields in structures, simulate the S parameters, and provide radiation parameters and characteristics of antennas. HFSS is used to simulate transmission lines, such as rectangular waveguides, which is something we'll be doing in this project, but it's also used to simulate antennas and radar cross sections. And in this slide, I provided some examples of what HFSS is capable of doing. So in this project, we will be working on two designs. The first is a rectangular waveguide, and the second is an impedance matching design question. So in this demonstration, I will show you how to design these structures on HFSS and how to simulate them. And then in the assignment, you will be doing a little bit of comparison between theory and simulations. So the first structure that we will simulate is this rectangular waveguide shown here. And from HFSS, we will determine the fundamental mode, or the TE10 mode cutoff frequency. And we will also plot the electric and magnetic fields of the fundamental mode inside the waveguide. And then for the impedance matching question, what we will do is we will use a patch antenna as our load. And from HFSS, we will determine the input impedance of the patch antenna. And then in the assignment, you will use this input impedance as the load, and then you will use a shunt stub to match the input impedance of the entire structure to 50 ohms. So if this sounds unfamiliar to you, that's okay. You will be learning about shunt stub matching in the course, and in the assignment will provide more detail on how to achieve this. But for the purposes of this video, we will just design the antenna without the stub, and we will look at the input impedance of the antenna. All right, so you should have access to a document that shows how to access the server, which has HFSS. So once you read that document and you have everything set up, you should be able to access the remote server. So it will look something like this. And the software that we need to run is the ANSYS electronics desktop, which you can find on the desktop, or you can also find it from the start menu here. So if you search for ANSYS electronics desktop, you should be able to run it. So if this is the first time you use HFSS on the server, you may get some windows for settings, such as choosing the working directory. So you can set the working directory as the H drive, and it's a simple setup procedure. But if you have any questions, you can reach out to me. So once you open HFSS, you will see here that it has created a project. So what you can do is you can save this project in the H drive. And the reason why I ask you to save it in the H drive, so the H drive should be easily accessible from here. And the reason why I ask you to do that is because the H drive can be accessed from any server in the VLSI network. If you save it on the desktop or on the C drive, you may not be able to access it and it may be lost. So always use the H drive for your files. So what you can do is you can go there, you can create a folder if you like. I will call this, for example, the HFSS intro. And then in that folder, you can save the project. So I can call this the HFSS project 3909. So this project, you can create multiple designs from the ANSYS package, but the one we'll be using in this course is the HFSS software. So you can click on here and just click on HFSS. And this will create an HFSS design for you, as you can see here. So we will start by working on the rectangular waveguide, and then you will see the design steps that we need to do. So the rectangular waveguide is simply a box. So what we need to do is to draw a box. So go in here, so draw box, and we will be doing the positioning and the sizes of the box using variables. So what I want you to do for now is just click 3 points on the design. So the first 2 points will create the first 2D plane, and then the third point will create the 3D structure. And it doesn't matter where you start and where you end. We will figure this out in just a minute. But what it essentially does is it creates a box, as you can see here. The box is made of vacuum, which in our case is okay because we are designing an air or vacuum rectangular waveguide. So this box has a name, which you can change. And then create box here, this is where you define the position and the size of the box in the X, Y, and Z dimensions. So what we'll do is we will start, so we want to center the box on the coordinate system. So what I will do is I will create variables, and these variables will be really helpful when you make your own design for the assignment, because you can simply change the numbers in the variable window, which I'll show you in just a second. So what I will do here is I will create a variable called waveguide A, so that will be the A dimension of the waveguide. So what I will do is I will start at minus waveguide A, and then for the y axis I will start at 0, and for Z I will start at minus waveguide B. So once you create a variable HFSS and you press enter, HFSS will ask you what is the value of this variable. What I will do is I will choose A to be 20 millimeters. So if I type in 20 and then HFSS will recognize this as millimeters. So click OK. And then for B, I will make that as 10 millimeters. So for the X size, that will be waveguide A. For Y size, that will be the length of the waveguide. So I can create a new variable called waveguide L. And I will make that 15 centimeters. So if you click centimeters, if you click tab, then it will recognize it as centimeters. And then for Z, that would be waveguide B. So this has created the structure. So in order to see the full picture, what you can do is click anywhere here in the model window, and then Control D on the keyboard should bring the full structure out to you like that. So it's not really centered on the axis, so I may have done a mistake there. So yeah, what I want to do is actually start at waveguide A over 2 and waveguide B over 2. So as you can see there, if I rotate it, you can see the waveguide is centered on the x-axis, starts at y equals 0, goes the length of the waveguide, and it's also centered on the z-axis, as you can see here. You can always change the orientation, look at an isometric view. So these parameters have now identified the starting and end positions of the waveguide. And as you can see, all these variables, if you made a mistake in assigning the variable, if you click on the design window, you can see the variables that we created over here. So for example, if I made a mistake in B and I want to change this to 15 millimeters, I can just enter 15. And then as you can see, the height will change. I'll change that back to 10. You can also change the length of the waveguide, as you can see here. Change that back to 15. And you can always play with these variables after you've designed the structure, which is really helpful because the waveguide design that you will be making for the assignment will have different dimensions. So if you've created this once, you can just go back and change the variables without having to redesign it. And other things you can do here is you can change the color of the box. So I can give it a different color, like here. I can also change the transparency, so I can see through the box. This will be good when we look at the fields. And then you can always just escape to look at the structure. All right, so the first step is creating the rectangular waveguide model. The second step is to assign the faces of the waveguide as metal, because our rectangular waveguide will have metal faces. So what you can do on HFSS is if you click F on the keyboard, you will be able to select faces. Another way is to right click and then you can go selection mode and faces. So either way you do it, you can select the faces of the waveguide. And what we want to do is we want to select the sides and the top and the bottom walls and set those as metal or a perfect electric conductor. So what I can do is if I press Control on the keyboard, I can select multiple faces. And then I can rotate. You can also do the rotation with the wheel of the mouse if you're using a mouse. And then I press F again, Control, Control. So what I've done here is I've selected the 4 faces of the waveguide, as you can see here. And what I will do is I will set those faces as perfect electric conductor boundaries. So if I right click, if I go under boundary and then perfect E and then OK. And what I've done here is if you click on the design, I've created a perfect E boundary for the 4 faces that I have selected. So these will be the faces of the waveguide. All right, so next thing we do is we want to assign ports. So a port is simply a location where the energy flows in and out of your structure. So for a rectangular waveguide, what we want to do is we want to assign these faces of the waveguide. So this face over here and this face over here as our wave ports. So what you can do is you can just select the face, right click, assign excitation, port, wave port. And you can leave the name as 1 and the number of modes as 1. So what that means is it will excite the first mode of the waveguide, which is the fundamental mode, which is the one that we care about in this project. So you can leave the integration line as none. Characteristic impedance, you can select that as Z wave. Then click on next. And we don't want to renormalize, and we're not going to de-embed in this design just yet. So I'll do the same thing for the other port. So select faces, click F on the keyboard, that will allow you to select face, right click, assign excitation, port, wave port, and again that will say this is Z wave, this is port number 2 now. Next, don't renormalize and finish. All right, so now these ports, you can see them under excitation. So if you click on 1, you can see where the first port is. If you click on 2, you can see where the second port is. All right, so now the next step is to set the analysis parameters. So under analysis here, if you right click, add solution setup, then advanced. So the first thing we want to set is the frequency. So for rectangular waveguides, that would be the maximum frequency that we're interested in simulating. So in this case, my maximum frequency of interest is 20 gigahertz. So I'll just say 20 here. Maximum number of passes. So the way HFSS works is by meshing the structure, running a simulation, and then meshing it again, running a second simulation, and then finding the difference between the 2 simulations. And if the difference is large, then it keeps going. So it's sort of it's a numerical solution technique. So the number of passes is how many times it's going to mesh the structure before it stops. So a good number to start with here is 15. So what it says to HFSS is that you can only mesh the structure 15 times and then you stop. Of course, by increasing the number of passes, you give it a more chance to converge to give you more accurate results, but 15 is usually a good number. Maximum delta S is the maximum error you can tolerate. So S refers to the S parameters. So the maximum delta S is the maximum change in the S parameters that you can tolerate. So 0.01 is usually an acceptable error that we can tolerate and get accurate results. Next, you go under options. So what we'll do here is we'll set the minimum number of passes to 6. And what it means is HFSS will run at least 6 times. So this ensures that the simulation has a chance to converge. Minimum converged passes, we'll set that to 3. So what that tells HFSS is that you have to converge on the number, which is 0.01. You have to converge on that 3 times in a row before you stop the simulation. So all these settings that we're doing is just ensures that the results that we get from the simulation are accurate. And once you start working with HFSS, you start to get a feel of what numbers are best to use. And we will check the convergence criteria and convergence parameters before we look at the results. All right, so these are the 2 settings that you need to care about. So you can click OK. Then what it will ask you here is to set the frequency sweep. So you basically set the start and end frequencies that you're interested in looking at for the results. So you can leave the sweep type as interpolating, and let's say here we're interested in frequencies from 1 to 20 gigahertz, and instead of a linear count, I'm going to do a linear step, and let's say in steps of 0.25 gigahertz. So you can see here that will mean 77 frequency points that we're going to simulate. And you can preview here, and you can see that we're going in steps of 0.25 gigahertz from 1 all the way to 20 gigahertz. So you can close that and you can click OK. So you should be able to see this under analysis. So the setup is created here. So if you double click, you can see the setup information. And if you made a mistake, you can always go back and change it. For the sweep, so our sweep's called sweep, and it's from 1 to 20, as we've seen before. All right, so once you've done that, you're ready to simulate the structure. So if you click on the design, and one thing I'll do here is actually I'll rename this to something meaningful. So I'm going to say rectangular waveguide. And then if I click on simulation, I can validate the design. So this just tells me that everything is good to go for the simulation. And what you can do is you can click on Analyze All from here, or you can right click and Analyze All from here. And as the simulation is going, you'll be able to see the progress here. So you can see the number of passes that HFSS is doing. You can also look at results, solution data, conversions, and you'll see the number of elements in the meshing, the maximum delta S that we talked about, and you can even see the plot of conversions. So the 0.01, that's our convergence criteria, and you can see HFSS has achieved that convergence within 6 passes. So we'll just wait for the simulation to finish. All right, so the simulation has finished, and I don't see any errors in the messages here. If there are any errors, they would be under the project name on this side, so everything has gone fine. So now what we want to look at is the cutoff frequency of this waveguide. One thing that can tell us the cutoff frequency is the transmission between port 1 and port 2. And this transmission is called S21 in the S parameters, and that's what we're going to plot now. So if you go under results here, if you right click on results, create modal solution data report, and then rectangular plot, we're interested in looking at S21. So S21 is the transmission from port 1 to port 2. And by looking at this transmission, as you will see in a second, we will be able to identify the cutoff frequency of this waveguide. And let's say we want to look at S21 magnitude, and the primary sweep is frequency. And we are taking this primary sweep for the first, for setup 1 sweep, which is from 1 to 20 gigahertz. All right, so let's plot that and see what it looks like. So as you can see here, from 1 to a little bit above 7 gigahertz, we have 0 transmission. So that means the waveguide isn't cut off. And then at some point, the transmission goes all the way to 1, so you have perfect transmission. So that tells us that the cutoff frequency is in this region, and more specifically, it's right at this point where you have power flowing inside the waveguide. So we can identify this frequency if we can add a marker here. So if I add a marker right at this point, and you can see here that the cutoff frequency of the waveguide is 7.75 gigahertz from HFSS. And of course, you can compute this cutoff frequency from theory, and then you can compare the two. Hopefully, they'll be similar. So that's for the cutoff frequency calculation. One thing we also want to do is we want to look at the field inside the rectangular waveguide for the TE10 mode, or the fundamental mode. So since this is the cutoff frequency of the waveguide, we know that this is the cutoff frequency of the fundamental mode. It's the only mode we simulated. So we can look at any frequency above the cutoff frequency and look at the fields inside the waveguide. But to look at the fields, we need to run something called a discrete sweep. So once we've identified the cutoff frequency of the waveguide, we can just pick any frequency above 7.75 and run a discrete sweep for that frequency, and then we'll be able to look at the fields. So what you can do is you can pick 8, 9, or 10, or any other frequency from here. But for now, I will pick maybe 9 gigahertz. So what I will do is I will go under the setup, and then I will add a frequency sweep. And I will do a discrete single point, and I will do, let's do a 10 gigahertz. And I want to make sure that we save the fields. And then OK. And then what you can do is right click on sweep 1. Now let's give it a name so that we can identify it later. I'm going to call this field frequency. So I will right click and then analyze. So HFSS will run the simulation for this frequency point. And since it's a discrete sweep and we save the fields, we will be able to look at the fields inside the waveguide. All right, so the simulation was quite fast because it already had the solution from before. So what we can do now is we can find the box, so that's the rectangular waveguide, right click, plot fields, E, and we'll plot the vector E. And here from the solution, we're going to select the field frequency. And of course, it's only 10 gigahertz. And we can click done. So as you can see here, this is what the vector field, vector representation of the electric field would look like inside the waveguide. We can do the same thing for the magnetic field. And remember, this is for the fundamental mode. It's the only one that we ran in the simulation. And perhaps since it's 10 gigahertz, it could only be the fundamental mode. So we'll do H, vector H, field frequency. And seems like the lines are too big. So what I will do here is for the H field, so if you double click on the legend, you can scale down the markers a little bit. Maybe that will allow us to see them better. And I will do the same thing for the E field. So if I double click, I'll just make the size slightly smaller, close. And what I will do is I will make the fields invisible so I can view them each separately. So if I right click here, make that invisible, I'll make that invisible as well. So if I click on that one, here you can see the electric field representation inside the waveguide. So you can take a look at multiple views. And then if I click on the H field, you can see what the H field looks like inside the waveguide. Better to see a top view, so you can see the H field is rotating this way around the electric field. And this would be the kind of picture that we would want to see in the assignment. And I also would likely ask you to compare this with, for example, a picture from the textbook to make sure that HFSS is doing the right thing. All right, so this is it for the rectangular waveguide design. Now we'll go into the patch antenna design. So what you should do always is to save the simulation, so you don't end up losing it. And of course, it's in the H drive. You should be able to access it from other servers if anything goes wrong with that server. All right, so for the patch design or the impedance matching design that uses the patch, what we'll do is we'll create a new HFSS design. And we will give that a name, so we'll call that impedance matching. So the first thing that we need for the patch antenna or the microstrip transmission line, which we're using as part of the question, is to create a substrate. So substrate is simply a box. So you can put a box somewhere there. So the difference between this one and the rectangular waveguide is that our box will be a dielectric. So we will be using a dielectric called FR4. So right here under material, you can click on edit, and then this will bring you to a window that allows you to select what material you want for this box. We can search for FR4, and then you find it here. So it's FR4 epoxy, which has 4.4 epsilon R, so it's the relative permittivity. loss tangent of 0.02, and you can see other properties there as well, but these are the two that we care about. All right, so if you click OK, that will change the material assignment to FR4, and then now we can create the box positioning and dimensions as we need. So for the position, what I will do is I will create a variable called sub w, which is the width of the substrate. So I'll just I'll go sub w over 2 for x, and then for y I will start at 0. For z I will start at 0 as well. So I'll select the width of the substrate to be 10 centimeters. And then for x size that will be sub w. For y size that will be sub L, which is a new variable, and I will set that variable as 14 centimeters. And then z size will be sub h, so it's the height of the substrate, and that will be 1.6 millimeters. So again, if I click anywhere in the window, Control D, we should be able to see the full design. And in case you missed it, these are the variable definitions, and these are the values of those variables. So again, just like before, if you made a mistake in the number, you can always change it. So I can make the 16, that would change the length of the substrate, and so on. All right, so now you have the substrate that the microstrip line and the patch will go on. So the next step is to create the line and the patch. So the line and the patch will be created using a sheet. So a sheet is a 2D structure as opposed to the box, which was 3D. And you can create a sheet, a rectangular sheet by clicking on here. And just like before, don't worry where you will put it. We will figure this out in the design window. And one thing you will notice is when you create a sheet, it doesn't have a material because sheets are not objects. But what it has is something called a boundary, and that's what we will assign here. So for the microstrip line and the patch, we will assign a perfect electric conductor boundary, which basically means it's a metal. So if you click on rectangular 1 here, you can right click, assign boundary, and then perfect E. Click OK. So this will give the sheet a boundary of perfect E, which means perfect electric conductor, and you can also see it under boundaries here. All right, so now we can create the microstrip line. So for the position, we'll create a variable called MSW over 2. For x, we'll start it at 0 for y, and for z, we will put it on top of the substrate, so that will be sub h. And then the width of the line is going to be 3 millimeters in order to get 50 ohms. So that's something I may ask you to verify in the assignment. But basically the width of the microstrip line of 3 millimeters on FR4 of a height of 1.6 millimeters will be a 50 ohm transmission line. So you can click OK. And then for the x size, that would be MSW. And then the y size will be the length of the line. So we will use a line length here. So we'll also create a variable, of course, because it's easier to work with variables. And that will be 95. Let's do 95 millimeter. Yeah. All right. So here you have the line. And one thing I will do actually is I will give it a different color so we can see it on top of the substrate. So I'll do that. So you can see here the line on top of the substrate. And again, in case you missed it, that's the definition of the line, position and dimensions, and the variables are here. And you can always change those variables if you've made a mistake. All right, so we've created the line. Now we need to create the patch. And again, that will also be a rectangle, so you can put a rectangle somewhere there. Again, we'll give it the right boundary definition, so that will be a perfect E. And we will do the positioning now. So for x, that will be minus patch w over 2. And for y, so we want the patch to start where the line ends. So the patch will start where the length of the line ends. So that will be MSL. And we want the patch to be on top of the substrate. So that would be sub H. So the width of the patch, I have calculated for my frequency of 2.5. Again, this frequency will be different for you when you do the assignment, but since you've created the design with variables, you can easily go back and change it. So I found the width of my patch to be 36.5 millimeters. So now for X size, that would be patch W, and for Y size, that will be patch L. That would be the length of the patch. And I found my patch to be of a length of 28.2 millimeters. And again, I will give this a different color so that I can see it on top of the substrate. All right, so here's the patch, and here's the definition again in case you missed it. And here are the variables of the dimensions of the patch. And the good thing about defining all these with variables is if you want to change the length of the line, everything is going to move with it. So if I put this as 80, then the patch is going to move with the line. I can put this as 95, I think that's all for that. If of course your patch dimensions will be different than mine when you do the assignment, but you can always run the simulation, and then when you find your own dimensions, you can just come back here and change it. So if this is 40 for you, for example, you'll just be able to change that. All right, I'll just go back to my old numbers. All right, so we've defined the patch, we've defined the substrate. The next thing we need to do is to define the bottom of the substrate as a perfect electric conductor as well, because that will be our ground plane. So I can rotate here, press F on the keyboard to select faces, select the bottom face of the substrate, right click, assign boundary, perfect E. Now you have the definition of the bottom here, and you can see all the boundaries here. So the boundary for the line, for the patch, for the bottom of the substrate. And the last thing we need to do for the patch is to actually create a vacuum box to cover the top of the patch, because in reality this patch will be operating in air or vacuum because it's a microstrip line. So what I will do is I will create a box around the patch, and then that box will be vacuum or air, and then put radiation boundaries around that. So I'll show you what I mean in a second. So I'll just create a box here, and first I'll just make it more transparent because we want to see what's inside the box. Of course, it's the microstrip line, and I will leave it as vacuum. And for the dimensions, it will be the same size of the substrate in the XY plane. So that will be minus sub W over 2, 0, and I'll start at 0. This will be sub W. This will be sub L. And then for the height, I will make that create a new variable called airbox H. And let's make that 35 millimeter. All right, so we've created an airbox. And what we're going to do is we're going to use one side of that box as the wave port, because we need, again, for HFSS, we need a place where the energy will flow. And in our case, that would be at the end of the transmission line here. That's you can think of it as that's where the generator would go. So this face I will assign as a wave port. So again, click F on the keyboard, you'll be able to select this face. You can right click, assign excitation, port, wave port, and you can leave these parameters as is. And one thing I will do though is I will renormalize everything to 50 ohms. And the reason I'm doing this is when we look at the S11, or the reflection coefficient, which we'll see on the Smith chart, I want everything to be normalized to 50 ohms, which is the impedance of my line. But it also allows us to do the matching on the Smith chart from HFSS. So it allows us to look at the S11 and then be able to know exactly what the load impedance is that we're looking at. So make sure that you renormalize to 50 ohms. And the de-embedding we will use, but not yet. So you can leave it unchecked. So you can say finish. And if you go here, you will see the wave port defined. And what I will do is I will define the rest of the waveguide faces. Sorry, not the waveguide, the rest of the airbox faces. So everything except the bottom and where the wave port is, I will assign this as a radiation boundary. So I can select this, and then Control allows me to select all the other faces. So F. So as you can see here, I've selected 1, 2, 3, 4 faces except where the wave port was, and I did not select the bottom as well because the bottom is going to be the ground plane or the PEC that we defined. So once you've selected those faces, you can right click, assign boundary radiation. So you've assigned the radiation boundary here. And the next step would be, so you've defined all the PECs, right? All the radiation boundary, you've defined the wave port, you've renormalized 50 ohms. So when we look at the Smith chart, we'll see everything renormalized to that number. So the next thing is to set up the simulation analysis. So we'll go there, we'll add solution setup, advanced. And for the frequency, you will put the frequency of the design of the patch that you will use when you look at the assignment document. So for me, in my case, that was 2.5 gigahertz. So when you follow this video, you can use 2.5 for the numbers that I used. But when you do the assignment, make sure to change this frequency to your design frequency, which would be something different. So I'm using 2.5. Maximum number of passes, I will do that as 15 like before. Maximum delta S, I'll do 0.01. Actually, what I will do here is I will change the maximum number of passes to, let's say 20, give it more chance to converge. And I will leave the maximum delta S as is. Minimum number of passes, I will do 6, and minimum converged, I will do 3. So click OK. And we don't actually need a frequency sweep because we're interested in the results at one frequency, which is the 2.5 gigahertz. So we can just cancel that. We don't need a frequency sweep. So the only frequency that we care about is the 2.5 gigahertz, which we will look at the S11 or the reflection coefficient at. All right, so once you have all that set up, we'll make sure that you save the design. And go in simulation, validate, make sure everything is good, everything is green, and then you can analyze that. So you can say analyze all. And just like before, while this is running, you can see the process going on here, but you can also click on results, solution data, and you can see convergence parameters as they happen. So you can see there our convergence criteria, which is 0.01, the green line. And you can see as the number of passes increases, we're slowly approaching that convergence criteria. You can see here we've converged at 1 point. So our target is 3 consecutive passes where the results converge. So we'll see if it keeps under there, or if it goes up, then it will reset the counter. And as you can see here, we've converged 3 times at 19 passes, so the simulation stopped. Perfect. Okay, so the result that we will use from this simulation is the reflection coefficient, which is basically the S11 of this port. So if you go under results, you can right click, model solution data report, and Smith chart. So we'll plot the S11 on the Smith chart. So S11 is the reflection coefficient that you've learned about in class. So we'll create a new report here, and you can see there the input impedance, or I should say the reflection coefficient of the patch at the end of the line is at this location. So from there you can also find the input impedance of the patch. So I can create a marker. So, and when I say the input impedance of the patch, I mean the impedance at the end of the line. Actually, what I will do before creating the marker, let me just close all of that. I will open this. I will open that and be tiled vertically. So, click here. All right, so this is the point, and remember this is at 2.5 gigahertz. This is my frequency, which when you do the assignment will be different for you. So make sure that you change that. I'm just gonna do that. Perfect. All right, so the wave port right now is at this location. So all the results that we're viewing are at this reference plane. So this point, which I can add a marker to, I can click right here, is 2.5 gigahertz, and just extend that here. All right, not cooperating. Okay, there you go. All right, so we are on the Smith chart. We are at point 1.64 minus 1.09 J. So from this point, and knowing that we renormalize to 50 ohms, you can multiply by 50 ohms, and then you can find what the input impedance at this reference plane is. But now the question is, how do we find the load impedance? So what you can do is, of course, you can, knowing the length of the line, you can go back to the load, so you can rotate on the Smith chart and find what the load impedance is. But on HFSS, it's actually quite simple. All we need to do is change the reference plane so that it's at the patch, and this will tell us the load impedance, which in this case is our patch element. So what I will do here is I'll just do a top view so that we can easily see it. Actually, I'll zoom out here. All right, so what we need to do now is to de-embed the wave port by the length of the line so that all the results we view are at this location. So if you go on the wave port, and I'll just double click on it so we can go to the post-processing. And what I need to do is I need to de-embed by a distance which is equal to the length of the line. And if I click OK, what you will see here is that the wave port, the reference plane, has now been moved so that it's at the patch. So now the results that we view from the Smith chart, which by the way has changed if you've noticed, this will be the load impedance because now we are looking at the patch alone. So now the load impedance is 0.838 minus 1.08 J. So this is the load impedance of the patch, right? And what you want to do in the assignment is, knowing this load impedance, you want to find a location along this line that you can add a stub so that the input impedance without the de-embedding, so the input impedance of the whole line, is 50 ohms. And what it means, 50 ohms, is that it's at the center of the Smith chart. So when you get the assignment document, you'll be asked to perform this in using calculations, using the Smith chart on paper, and then you want to find the dimension or the location, so the distance away from the patch, and the length of the stub that will achieve this matching. So you will do this on paper, and then you will do it in HFSS, and then compare the two results. All right, so just watch that part of the video about the de-embedding. So where you view the results is important. So if I de-embed to the patch, I'm looking at the load. If I do not de-embed, so if I just cancel, not the renormalization, the de-embedding. If I cancel the de-embedding, what I'm looking at is the result of the input impedance, including the line. All right, and once you're done that, so I will not show you the matching, so that will be part of the assignment, but the stub will basically be another piece of PEC. So when you do want to add the stub, I will just show you quickly how to do that here. So the stub will just be another piece of okay, let me just save the results. So what I will do is I will add a piece, and if it asks you, do you want to create a non-model object, you need to say no, because any object we want to create, we want it to be a part of the simulation. And a non-model object is an object that is not considered by HFSS. So I'm going to say no to that. All right, so basically we want the piece of transmission line. right here. So what you need to do is you need to create this piece. You need to set the location, right, based on the values that you get. So of course it will be, for example, it will be on top of the substrate, right? So the position will be on top of the substrate. It has to be in the X dimension. It has to start from MSW over 2, and not for Y. Sorry, this is so for Y this would be, let's say, the how far away from the patch. So this would be patch. I should say MSL minus, let's say, separation. I'll call it sep. So that's how far away from the patch. So let's say this one we want it to be 10 millimeters away from the patch, and for X this would be MSW over 2. And the X size will be, I'm going to call it the stub L. So let's say the length of the stub is also 10 millimeters. And the Y size will be actually the same length of the line. So why do we, sorry, the same width of the line. Why do we want to use a line of the same width as the original line? So that's something I will let you think about. So this line is 3 millimeters, and we want the stub to also be 3 millimeters. So I'll let you think about why we need to do that. But basically this will be the line. Of course, it has to be a PEC line. So we'll do that. And so I'll give it a different color so that you know it's different from the other one. So that's different as in it's the stub, not the transmission line. All right, so now if I do some measurements here, actually I'll just confirm. 1 second here. So that'd be stub L, and actually I will do this as minus, so it goes the other way. So if I do a measurement from the end of the patch to the line, this should be 10 millimeters, as you can see on the top left corner. And if I do a measurement of the length of the stub, from here to here, this also should be 10 millimeters. All right, so I showed you how to model the stub on HFSS. So of course the length of the stub and the distance from the stub to the patch, that's something that you would have to calculate using the Smith chart, and then do that on HFSS. All right, so this is the end of the demo. Make sure that you save the file. And one thing that you should always remember to do is when you're done using HFSS, make sure you close it. And the reason is, if you have it open, you're holding the license, and we have a limited number of licenses, and there's many people that want to use HFSS. So once you're done, save the project, and you should be able to still access it, and just close HFSS. And if you have any questions and you want to send me the file, what you need to do is just send me the HFSS. So if I go HFSS Endro, all I need is this file. So there's 2 files that will be created in the folder. So there's the project file, which is just, the type is ANSYS Electronics Desktop file. And then there's this file, which is .aedt results. This one has your data, and it could get quite big. So I don't need to see this file. If you want to send me the project file, just send me this one. All right, so the assignment will be posted sometime next week. And if you have any questions, you can let me know. Take care.